Okay, on to question 5, and this is the specialist only part of the paper. So we've got it says explain the direction of the electrostatic force exerted on the ink drop by the charged plates, right? So we've got to explain, but then also it doesn't tell us which way it's acting, right? So we do need to say which way it's acting, right? So the force is going to act to the right, okay, and the reason why is because, well, you can either say that negative charge, like charges repel, so two negatives repel, or you could talk about the positive and the negative attracting, right? So either of those explanations is fine, right? But you do need to say which direction it's moving in, right? On the paper, draw the path of the ink drop as it falls between the charged plates until it hits the paper. So it's going to accelerate downwards, okay? So there's a force downwards on it, which is the weight, but then it's also going to accelerate to the right as well, because there's a force of electrostatic attraction on it to the right, okay? So I'm going to change the colour of the pen so that I can draw the path, okay? This is quite a kind of tricky thing to think through, right? Because initially it's going to start off with it's going to start off with zero speed in the x direction, right? So horizontally it's got zero speed, right? And also vertically it's got zero speed, right? But in the first, as it falls down towards the paper, okay, it's going to cover a little bit of distance in the first moments of time, but as it falls it's going to get further and further and further, right? Because it's accelerating as it falls, right? So that means that we're going to get a curved path like that. All right, it's actually parabolic motion. It moves in a parabola. That's not a beautifully drawn parabola. Maybe I should have another go at doing it. Okay, but you need a kind of curved path that looks like this. That's parabolic motion. And the other thing that's really important is it says, until it hits the paper. Okay, so if you kind of stop halfway between the plates, and then obviously you're not going to score both marks there, right? Right. Okay, so we're given the mass, and it's given us the horizontal force, the resultant horizontal force, and it's asking us to calculate the acceleration, right? So I know a formula that links those three variables together. It's sigma f equals ma, all right? And then I can substitute, or I can rearrange first. It's up to you. Okay, I think I'm going to choose to rearrange. So I'm going to do a is sigma f over m, and then I'm going to do my substitution. 8.5 times 10 to the minus 7 divided by 1.1 times by 10 to the minus 10. All right, and then if you type that carefully into a calculator using standard notation, okay, then you're going to get your answer out, which is 7727.27 blah 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 blah, right? But remember, how many significant figures should we give our answer to? We've got to be guided by the question. So we look back at the question, and you should give your answer to the least precise of the input data. Now, both of those are to two significant figures, so the best answer that we could give is 7,700 meters per second squared. Initially it's got no horizontal velocity, right? So actually, that explanation that we had to do for part B, now that we're working through C and D, C1 and C2, it's starting to confirm that we got the right ideas here, right? Because it gives us this idea that initially it's got a zero horizontal velocity, and then the velocity is increasing as it falls because it's accelerating towards the right, which is why it kind of bends in that parabola shape. Okay, so no initial horizontal velocity, right? I'm going to start writing some stuff down. So u, the initial velocity is 0 meters per second, right? And we also know a, we just worked that out in the previous part of the question, right? There we go. And it tells us v, the horizontal velocity after passing through the charge plates, right? Okay, and it's asking for the horizontal distance, right? So that's displacement. So that's the thing that I'm looking for. So then what formula do you know that connects those four variables together? It should be jumping off the screen at you. It's v squared equals u squared plus 2as. Okay, so substituting carefully, 3.9 squared equals 0 squared plus 2 times by 7700 times by a. Okay, that term just disappears. Okay, and then we type it all into a calculator and do the calculation, right? And we're going to get 9.9 times by 10 to the minus 4. All right. And that's in meters, of course, right? Because if you look, you know, that's in meters per second, that's in meters per second squared, that's in meters per second. Okay, so we're going to get our answer out in meters, right? And then we're going to convert that into millimeters, right? Now, you know, maybe you can do that really easily in your head, okay? But there is a little trick that you can do using your calculator, right? Have you ever seen the ENG button on your calculator? Okay, it stands for engineering, right? And it's a way of quickly moving between millimeters, meters, kilometers. You know, like you can do it just by pushing this button, right? So if you push the button, then you get 990 to the minus 6. Oh, that's not really helping us, because that's telling us that it's 990 micrometers. If you push it again, then you get 0.99 times 10 to the minus 3, right? And that is useful for us, because 0.99 times 10 to the minus 3, 10 to the minus 3 of a meter is a millimeter, right? So that means that it's 0.99 millimeters. Okay, just have a play around with the engineering button. Okay, and then the other way that you can do it is push Shift Eng, and it will make it go the other way for you, right? So you can look at how many kilometers it is, okay, and how many meters it is, and how many millimeters it is, how many micrometers, how many nanometers, how many. Yeah, there you go. Have a bit of fun with that new button on your calculator. Not quite at the end of the question yet. Let's have a look at this. Explain how another ink drop could be deflected in the opposite direction. Okay, so opposite direction by a greater distance using the charge plates, right? Okay, and this is a 2 marker, right? So, if we want it to go further, then what are the things that we need to change in here, right? Well, if you want S to increase, okay, you're gonna have to increase the acceleration on it, right? And the way that we can increase the acceleration on it is to increase the resultant force on it. Or, interestingly, you can either make this number on the top bigger, or you could make this number on the bottom smaller. So some of you talked about using a smaller ink drop that would get greater acceleration on it, which is a good idea. Or you can talk about increasing the force on it, right? So to do that, you could increase the charge on these plates, or increase the voltage on the plates. Okay, that would increase the charge on it as well. All right. it's a little bit outside the realms of the IGCSE specification, okay, but increasing the distance between the plates doesn't actually increase that force, all right? Much more about that when we get into IB, higher level physics, okay? But yeah, increasing the distance between the plate, that's not going to do what you want. And then the other part of the question was, how do we make it move in the other direction? Well, you can just make it positively charged, right? And then you'll get the reverse parabola. It'll go in the other direction. So that's one way that you could do it. Or you could switch over the polarity of these plates. That would have the same effect. So you can either change the charge on the ink drop, or you can reverse the polarity on the plates. Okay, so yeah, 1 mark for talking about how you change the direction, and another charge for how we get a greater distance. And we get a greater distance by increasing the force, or a sensible way to increase the force. Okay, done for that question.